Dear all, good morning. Now our lecture is QR factorization of a matrix. This is the application of Gram-Smith method. In this lecture, we are going to discuss how to factorizing a matrix. You can say this is a factorization or QR decomposition. You can say this is QR decomposition. How to decompose a matrix to QR. This is a concept in this lecture we are going to discuss. Now, theorem. For the theorem, let A belongs to M, that is n by n matrix. Let A be invertible matrix. Then there exist matrices Q and R. There exist matrices Q and R such that A equal to QR. This is our QR. Where what is the Q? Where Q is orthogonal matrix, and R is upper triangular matrix. Upper triangular matrix. Now let's see how to factorize this one. This is Q of orthogonal and upper triangular matrix. A is given matrix. Already you know this orthogonal matrix means Q transpose Q equal to identity. In upper triangular means below the diagonal elements are 0. Here A be invertible matrix. Which is proof as A is invertible. Invertible means it's invertible. Invertible means it's columns n by n matrix. Its columns it form a basis of Rn. It's invertible matrix. Invertible matrix. Its columns form a basis of Rn. Its basis. Now we take these columns of A, or consider the columns of A or U1, comma U2, and so on UN. I'm considering columns of A are columns, n by n matrix. That is, you can say matrix form that A equal to U1, U2, and so on UN. Each column, n columns. This one. Now here we are using Gram-Smith process. This application. So, so on application of Gram-Smith orthogonalization process. This set. Now we take the column set. This set U1, U2, UN gives. Last class we discussed gives on orthonormal basis set W1, W2, and so on Boolean. This is the basis of Rn. This orthogonal set are also Rn. Column sets are same. Satisfying, satisfying linear span of double one. Sorry, linear span of u1, u2, okay, whatever. Un equal to linear span of w1, w2, wn. This one. Already you know this one. The graphs with any linear independent set, linear span is same as the linear span of orthonormal, orthonormal vectors. This one. Now further, proceed further. Now take q equal to, yeah, we know this orthonormal basis q1, w1, w2, w1. Now take this is orthonormal columns q, w1, w2, and so on, w. Take this one. Then by orthonormality, by orthonormality of this set w1, w2, wn, the orthonormality of this set implies what the q transpose q. Q transpose this is a q transpose means each columns are transpose. W1 transpose, W2 transpose, and so on, Wn transpose into Q. W1, W2, Wn matrix. Now what is the multiplication? W1 transpose W1, W1 transpose W2, and so on, W1 transpose Wn. Next to W2 transpose W1. Next to W2 transpose W2. W2 transpose, and so on. That last vector is Wn transpose W1, Wn transpose W2, and so on, Wn transpose W. Yeah, this is the one. Now you know this is orthonormal vectors. When the orthonormal vectors, product of orthonormal vector, the same vector is 1, and the remaining vector W1, W2 is 0. These all are zeros. Only diagonal elements are 1. All are 0, diagonal elements are 0 means this n by n matrix. That means we get In matrix. That means Q transpose Q equal to In. See, now our aim is find to R. Similarly, Q transpose also In. We will discuss that next. That means it's orthonormal vector, orthogonal matrix. Q is orthogonal matrix. Yeah, we need to show that u1, u2, un equal to w1, w2, wn. That orthogonal the Gramsci process, yeah, that any linear independent set it's converted to some orthonormal basis. Suppose it's converted in matrix, so that means A and Q. It's converted to A to Q require another matrix. That matrix is the R. Yeah, that means we don't know this unknown matrix. I'm taking this is some upper triangular matrices. I'm taking alpha 1 1, alpha 1 2, and so on. Alpha 1 n 0, alpha 2 2, alpha 2 n, and so on. 0. This is alpha n n. Upper triangular matrix. Yeah. Now what are the unknowns? Alpha 1 1, alpha 1 2, alpha. We need to find this one. Now here is A equal to B. Yeah, note that this is u1 belongs to, you multiply this one, u1 equal to u1 is w1 alpha 1 1. That means u1 belongs to linear span of W1. W1 is a orthonormal vector. That implies already you know this one. When that any vector belongs to linear span of set, suppose V vector, linear span of these vectors are orthonormal vectors in this set. We can write V equal to, so I is equal to 1 to n V comma W comma W comma W. That's the linear combination of this one, this vectors. Now where this is the constant, this is some number. Yeah, this theorem we discussed in the first lecture in this unit. Now you can refer that one. Here that one only one vector. That means alpha 1 1 into W1. U1 is in the span. That means we get alpha 1 1 is U1 comma W1. The same as U2. What the U2 belongs to? Linear span of W1 comma W2. And W1 comma W2 is an orthonormal set. We get the same thing. Then we get here alpha 1 means alpha 1 to W2, W1, alpha 1 to W1 plus alpha 2 to W2. Now we read what is alpha 1 to alpha 2. We get alpha 1 to equal to linear span, this is U2. That means we get U2 W1 and alpha 2 to equal to U2 W2. This one. So in general, same procedure. In general, for any fixed I, suppose Ui belongs to linear span of W1, W2, Wn up to Wi, and the set W1, W2, Wi is an orthonormal set. And then we get now alpha from Ji equal to alpha Ji is equal to we get Ui comma Wj, yeah, where 1 less than or equal to what we require, which one is greater, 1 to 2 2. That means I is more, less than or equal to up to I. So if we take alpha 1 1 U1 W1, alpha 1 2 U1, alpha 2 1 yeah, alpha up to I. Suppose I is 1, this is 1, alpha 1 1, this is to alpha 2 1. Yeah, up I, J is 1 1 2. This 2 means 1 to U1 U2 W1, 2 to U2 W2 we get this one, U2 W2. But for any one we get this one. Now we get each constants, that is alpha 1 alpha 2 to up to whatever, any number. So you can extend to up to nth one also. Any I, it's I. You can take I is and extend it to n also. Yeah. Therefore R equal to alpha 1 1. Alpha 1 1 is U1 W1. Alpha 1 2. That is U1 U2 W1. So on. So nth one is Ui W1. And so on. Next this one. alpha 2 to U2 W2. This is UI W2 and so on. Okay, its last one is okay. If we take nth one, nth one is UI W. Yeah, at last one is this is nth one UN W. That's the one we'll get. Okay, you can write this is UN W1, UN W2, UI W N. Like this. The same as the inner product, right? This is the W1 U1 inner product. You can write W1 transpose U1, W1 transpose U2, and so on. W1 transpose UN. This is 0. W2 transpose U2. So W2 transpose UN, and so on. This is the upper triangular matrix. This one UN WN transpose UN. The one. That means this is A is equal to QR. Here Q is orthogonal matrix, R is upper triangular matrix. Now observe here, observing from this theorem, observing. Observe. First one. Now we are Q transpose. What about Q transpose? When you take Q transpose, Q is the W1 W2 WN. Q transpose is the W1 transpose, W2 transpose, and so on, WN transpose. Now if you multiply this one, it means we get W1 W1 transpose plus W2 W2 transpose, and so on, WN WN transpose. See here Q is a square matrix. We know this orthogonal matrix. Orthogonal means Q transpose Q is also identity, that IN. Observe here this one W1 W1 transpose. What does W1 means? W1 means n by 1 column matrix. N by 1. W1 and 1 by n. That means you get n by n matrix. Each one is n by n matrix. This is the n by n matrix. Total rank is 1. That means each rank is 1. Now that is we have written this IM. We have written the identity matrix matrix IN. How we written as a sum of n, sum of rank 1 matrices. Sum of n rank 1 matrices. Yes, this is rank 1 matrices. Now observe here this one. Each I, this matrices. This is one of the matrix. Each one is the matrix. Each one is n by n matrix. Each I, for each I, 1 less than or equal to I less than or equal to n, and each of these matrices, I'm taking capital Pi is equal to double I transpose, or this is symmetric and idempotent. Symmetric and idempotent matrix. You know this symmetric and idempotent, hence they are projection matrices. Projection matrices. The projection matrices. Each one is the projection matrix. Each one is the projection matrix. Yeah, sum of all projection matrix again projection matrix. That means when that columns are already, I told you, when that uh, all columns are linearly independent, the column space generating Rn, in that case projection matrix is identity matrix. That means total column space generating. In that case projection matrix is the In. So which column space is not generating, the projection matrix not identity. We get projection matrix uh, a number of column space, number of linear independent of column space of rank matrix. If the number of linear independent columns 2, we get projection matrix of rank 2 matrix, like that one. Now one, any vector, u belongs to Rn. Suppose I am taking any vector u belongs to Rn. Now uh, note that note that this PIU equal to WI transpose U into WI. This PI, that means you get small pi projection. That's a projection. This one. Yeah, what that means was the pi, capital Pi projects any vector on Rn space generated by if it is generated by Wi by W. That means projection. Each one is a projection, like projection onto a line. Each one is a projecting. Suppose it's a generating each say W1, W2, W up to Rn space. Yeah, first one is generating first vector, second, so on. That means each one is generating any vector Pi. Any vector on Rn is generated by Wi. The total is generated. One is generated W1 also. Column, second column, and up to so on. Yeah, this is the thing. Now one more observation you can observe. If we are writing A is equal to QR, the QR decomposition, where Q is Q transpose equal to identity. What about Q? It's an invertible orthogonal matrix. We know the determinant of orthogonal matrix always plus or minus 1. It's invertible matrix. That means Q inverse equal to I transpose. I transpose. Now we need to find this Q. We know A is the linear independent vector, Q is the orthogonal matrix. Now if you multiply with Q inverse, the Q inverse of A equal to Q inverse into Q or Q inverse Q is identity. That means Q inverse, but we know Q inverse is transpose. Q transpose A equal to R. That means therefore Q transpose A. By using this one also you can find the upper triangular matrix R. Q transpose A. You can use that this method, that all finding that constant, or inner products we are writing U1 W1, that one, or if you know Q, R is the Q transpose A, the multiplication of transpose matrix of orthogonal matrix and given matrix. Find any method. Now we'll see some example. Okay, we discuss generalized one. This is a square matrix. If it's a square matrix like this one, well, matrix is not square. How to decompose? How to decompose? Yeah, suppose generalized QR decomposition. Next we'll discuss example. Generalized QR decomposition. What is the generalized? Let be an M-by-N matrix. M-by-N matrix. Then, then A equal to QR, where A is, sorry, where A is, where Q is, okay, one more. Yeah, let A be on M by N matrix. M by N matrix. Matrix of rank R, of rank or some particular rank. Yeah, that means some columns are not linearly independent. Some columns are depends on or then A equal to QR, where Q is on by R matrix, not orthogonal. This one, that is orthonormal columns, but Q is not orthogonal matrix. M by R matrix and R is M by mat, and one more thing, this is M by R matrix and M by R matrix with Q transpose Q equal to identity IR, but not Q transpose. Only Q transpose Q is the IR, and R is M by R by N matrix with rank of R is R, both rank is R. See, we are getting, this is the QQ transpose. This is identity. This is the QQ transpose is the projection matrix. Here we get Q transpose Q identity. In this case, Q transpose Q not equal to N. This is the projection matrix. QQ transpose we get this projection matrix equal to this projection matrix. Projection matrix. See, when the terms are generating total Rn, the projection matrix is the identity. It's not generating total Rn. The projection matrix is the Q transpose Q. Q transpose. Sorry. What is it? QQ transpose, not Q transpose Q. Q transpose. Q transpose. The projection matrix. This is the thing. That means maybe M by N matrix rank is R. That is R less than M mostly. Minimum M comma N. It is a minimum of M comma N or less than or equal to minimum of M comma N. If rank M, we'll get that one. Suppose is less than 1, we get some M by R matrix. Suppose R rank is M, we get M by M matrix. M by M and M by N. R this one. Rank is less than M, we get M by R matrix. But with Q transpose Q is identity, but it's not orthogonal matrix. And we get Q transpose is the projection matrix. We'll see. I give example on this one. Now this application in the least square approximation we can use. What the least square approximation? Suppose Ax equal to B, not solvable. Well, we've taken this one, A transpose A x hat equal to A transpose B. X hat is least approximation, least square approximations. Already we know. Now by using QR decomposition also we can find least square approximation. This one A transpose A. What is the A transpose A? A is the QR. A transpose A is okay, QR transpose QR X hat equal to A transpose QR transpose into B. That implies R transpose Q transpose QR into X hat equal to R transpose Q transpose into B. Q transpose Q is the identity. Q transpose Q is the identity. Left cancellation R transpose cancel is identity. That means we get X hat equal to this upper triangular matrix with the diagonal elements are non-zero. That means inverse is exist. Means X hat equal to at R inverse X hat equal to R inverse transpose B. That means X hat is the R inverse Q transpose. So by using this one also we can find the least approximation solution. We know Q is the orthogonal matrix, R is the upper. That's inverse into Q transpose B. It gives effective best approximation. And one more, this decomposition. Whatever, I'll write this one. Okay, just I give idea. Decomposition is unique, not this one. Whatever, right? Whatever take matrix. Okay, both cases. Pure decomposition is unique. Okay, mostly we take this unique case is that when that is A is the square matrix. Unique. It is simple. Suppose we are writing. Suppose the decomposition Q1 R1 equal to Q2 R2. Decomposition expressing both are Q1 Q2 equal Q1 Y1 equal to R2. We are expressing equal to. Now in this case we know this Q1 Q2 are orthogonal matrix and invertible. R1 R2 upper triangle also invertible. Now suppose we are taking Q2 inverse Q1 R1. On the left side we can take R2 inverse Q2 inverse Q2 R2 inverse. So P multiply with the Q2 inverse, post multiply with the R2 inverse. This implies Q2 inverse, okay, Q1, okay, 1 minute. So multiply with Q1, Q1, multiply with R2. That means we get Q1 inverse, Q1 inverse identity. This is the identity. That means R1, R2 inverse, and it Q1 inverse Q2. This is the identity. Now R1 R2 inverse Q1 equal. This is the orthogonal. This is upper triangular matrix. Product of upper triangular, and this is orthogonal matrix. Upper triangle equal to orthogonal. It is possible when it is the identity matrix. See, when the identity matrix, therefore R1 R2 inverse equal to identity means equal to R1 equal to R2, and Q1 inverse Q2 equal to identity means Q1 equal to Q2. That means whatever you take, where Q's and whatever how many orthogonal matrices also take, Qi's and Ri's are orthogonal matrices and upper triangular matrix. Upper triangular matrices respectively. That means QIC are orthogonal matrices, RIC are upper triangular matrices. Yeah, this is the one that whatever QR decomposition is that's unique for square matrix. Now we'll see some example. Some example. Let A equal to 1 1 1 1 1 2 1 2 3 1. Yeah, right. Now this one. Then write in factorization or QR decomposition. Yes, QR factorization. Now write QR factorization. The problem. The solution. Now for QR factorization we require orthonormal vectors. Now use the Gram-Schmidt process. Let u1 equal to 1 1 1, u2 equal to 1 2 1, u3 equal to 2 1. Yeah, by Gram-Schmidt process, that you can find orthonormal base vectors or orthogonal vectors. If you know orthogonal vectors, you can write orthonormal vectors by dividing with length. Gram-Schmidt process, I am writing directly. We get, you can try this one orthogonal vectors. V1, I am writing V1 is same as the U1, 1 1 1. V2, now use the formula, we'll get U2 is 1 by 3 into minus 1 2 1 minus 1, and V3 equal to 1 by 2 into 1 0 minus 1. This form. This one. These are orthogonal vectors. Therefore orthonormal vectors are, therefore orthonormal vectors are, now divide with W1 equal to V1 by norm V1 equal to 1 by root 3 into 1 1 1. W2 equal to V2 by norm V2. This equal to this is the length, this one divided with 1. This is same thing. Numerator divided. The length is 6. 4 plus 1. 6. 1 by root 6 minus 1 2 minus 1. And W3 equal to V3 by norm V3 equal to 1 by root 2 into 1 0 minus 1. Yeah, this is the one. Yeah, therefore orthogonal matrix orthogonal matrix, okay, right, orthogonal matrix Q equal to, now write these columns 1 by root 3 1 by root 3 1 by root 3 Q. Next W2 minus 1 by root 6 2 by root 6 minus 1 by root 6 1 by root 2 0 minus 1 by root 2. Yeah, this one. Hence A equal to, A means given matrix, hence 1 1 1 1 2 1 2 3 1 is equal to Q. Q is this one, 1 by root 3 1 by root 3 1 by root 3 minus 1 by root 6 by root 6 minus 1 by root 6 1 by root 0 minus 1 by root. And R, what is the R? Okay, write one more. R is, you can write W1 transpose U1 W1 transpose U2 W1 transpose U3 0 W2 transpose U2, W2 transpose U3, 0 0 W3 transpose U3. So write this one. The Q same thing. And what about R? The W1 transpose U1. W1 now multiply. W1, so that is W1 this first column and in the U column. We get 1 by root Q and this W1 and this one U. That's 1 by root 3. 1 by root 3 will get next 4 by root 3. May I correct? 4 by W1 and U2. What the U2? U2 this one. 2 plus 1 plus 1. 4. 4 by root 3. Next this one is 6 by root 3. 0. 2 by root 6. Okay. 2 by root 6. Next multiply this one. W2 and U3. W2 and U3. 4 minus 2. 6 minus 1. Minus 3. Plus 3. 3 by root 6. 0. 0. This is you get W3 U3. Minus 1 2 minus 1 and 3 1. Minus 2 6 minus 1. W3 this one. That means U3 2 3 1. 0 minus 1. That's 1 by root 2. 1 by root 2. This one. This is therefore A equal to Q here. This is A, Q, this is the R. We written A is equal to QR decomposition. Or you can find here, this I find R this way, or you can find R equal to transpose here. We know Q and the transpose of this Q and multiply with A. You get that R. Now we'll now try examples. I'm writing that one. Okay. Now we see this one. Second example. Let A equal to 2 0 0 5 2 0 3 1 0 1 1 1. This is a 3 by 4 matrix. It's not a square matrix. Now find this one QR decomposition. Right? A equal to QR. I am giving answer. Q is I3 will get. And if Q is I3, R is A. Try this problem. So you take U1, U2, U3, U4. This out of 4 vectors, one of the vector is linearly dependent. Check which one is the linearly dependent. Remove that one and write that is the Q. Those vectors corresponding normal. No. And one same problem. Let's suppose take A equal to. Already you know when you are interchange that vectors, you get that orthonormal vectors also different. Suppose if you interchange this one, suppose you write 5 2 0 second column is first one and third one is second one 0 0. This one is third column 1 1 1. Let's see what happened. This was also one of the linearly dependent vector. Now find out which one is the depending vector. In this case, write A equal to QR. In this case, we get Q equal to by 29 by root 29 0 by root 29 minus 5 by root 29 0 0 0 1 and R equal to root 29 17 by root 29 . Okay, one more thing. This one, double one transpose u1. Double one is 1 by root 3. 1 by root 3, 1 by root 3. Actually, this is 3 by root 3, or you can say root 3. 3 by root 3. This one. 1 by root 3 plus 1 by root 3 plus 1 by root 3. Root 29, 17 by root 29, 10 by root 29. Yeah, we get this. We got 3 by 3. Next matrix, this is 3 by 4 matrix. 0, 0, 1 by root 29, 4 by root 29, 0, 0, 0, 0, 1. These are the matrix. You can try. Now another one. Find uh, column space A 1 1 1 1. Okay, we'll write this one. Let A equal to 1 1 1 1 minus 2 0 1 3. Then find projection of minus 4 minus 3 3 0 0 0 onto the column space of A by using orthonormal by using orthonormal. Now try this problem. For if interested, you can try last class problem also. Last class I given problem. The problems also can expand as QR factorization. If interested, you can try. You can take any problem, any independent vector. You can write QR decomposition. This is the application of Gram-Schmidt process. Now I am stop here. Thank you.